right, this is going to be part 2 of our wire resistance lecture. And not that the other one wasn't long enough, but I mentioned earlier that the American wire gauge came from a company called Brown and Sharp, I believe it was, or Brown and Stewart. I can't remember what the name of the company was, but nonetheless, they decided on wire sizes such that if you went up 3 wire sizes, you doubled the cross-sectional area. And back then, they only went up to size 4/0. They went up from very small numbers like 18, meaning it was a very small gauge wire, 16, 14, which you're familiar with, 12, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then 0. But that wasn't big enough, so they had 00, which they called 00, 3 zeros, 000, 40. Back then, that was the biggest wire they had, was 4/0. And so that was the biggest wire that was available back then. So the American wire gauge originally only went up to 4/0. And that's why, if you look at an American wire gauge table in the code book, it goes up to 4/0, and then it goes into cross-sectional area of 1,000 circular mils. Okay? So it wasn't part of our original wire gauge standard, and that's why it stops at 4/0. It's the old Brown and Sharp wire gauge, I believe, and like that. 4/0 has 211,600 circular mils, and we were looking at a problem earlier where I think we needed somewhere around 200,000 circular mils, wasn't it? And that was size number 4/0. Oh, that's 4/0. Okay, now let's look at the NAC chart, which is 31016, and you'll see on the far left the numeric values down at 18, 16, 14, and there are a lot of rules about these little wires that 18 and 16 can only be used for certain purposes, meaning, for instance, motor control circuit, which is going to be a very small current, and it's fused to allow using such a small wire. Generally speaking, for wiring most circuits, the smallest wire you can use is number 14 for most circuits, and for any motor circuit supply circuit, the smallest wire you can use is 14. But that's not the smallest wire you can use at all. It's just that there are only certain purposes you can use 16 and 18 for. Okay. In the left-hand column, you see the kind of wire. Look at the top of the column, and you'll see where you have, hang on one second. All right. So I can't pull up the internet, so we won't be able to get a picture of 31016. But if you look at page 321 in the 5th edition of STE, you can see a reprint of one of the code pages, and you'll find on the left is the wire size. And then at the top, I want you to notice there are 3 columns, and below each column it has a type of wire that's in that column. On the left-hand column, you've got 60 degree, and it says 140 degrees Fahrenheit because 60 degrees is centigrade. And it says down below that TW and UF. UF is sort of like an underground Romex, and TW is, well, it's a larger diameter insulation wire that's kind of an old school kind of wire. The next one is 75 degrees or 167 degrees Fahrenheit, and it's RHW, THHW, THW, THWN, XHHW, and ZW, and USE. I missed USE. And then the 90 degree column, which is 194 degrees Fahrenheit, we have a lot of kind of wires, TBS, SA, SIS, FEP, FEPB, MI, metal insulated, not metal insulated, mineral insulated, RHH, uh, RHW, THHN, THWN, and so on and down. And I want to tell you a little about some of those abbreviations. X means that it's a higher temperature, like the 75-degree wires will have an X in their title. And a very high temperature, a 90-degree temperature wire will always have XX, high temperature rating in their title. Also, the mineral that they're, or the type of material that they're insulated with will very often be part of their title, like R stands for rubber. MI means mineral insulated. Let's see here. T is thermoplastic, and so on. There's a lot of those that we want to include maybe a little later, and we'll talk about that some other time. X is cross-linked polyester, I think it is, but we don't need to know that. We just, not at the moment anyway, and we just need to know the ampacities and the duration factors. Now, the duration factors are down at the bottom of the column. Now, it doesn't show that in your book, not on that page anyway, but if you go over to where it says correction factors, the next page is 326 in the 5th edition, and it shows down at the bottom of the column what you have is a bunch of percentages. Ambient temperature, some very low temperatures, and then some very high temperatures. And they're just a multiplication factor. You take the ampacity of the wire and you multiply it times this. Now that's for a temperature, right? Now if you look at the next page on 327, you see the number of conductors, number of conductors. And remember, 1, 2, 3 for free, 4, 5, 6, 80%, 7, 8, 9 is 70%. Now the rest of this chart, you would have to look up because you'll never remember those, right? But let's look at a wire where we have a high temperature rating, and let's look at a T. Let's go back to the wire chart on 31016, which is back on 321, and let's take a 90-degree wire. Let's say we have a number 6. Number 6 at 90 degrees is worth 75 amps, right? Now let's look at that same wire. It's 65% duration factor at 61 to 65 degrees centigrade. So that means if you look at the column under 90 degrees C and look at the left column 61 to 65 and scan across, you see 0.65. That means that at 61 to 65 degrees centigrade, that wire is only worth 65% of its original ampacity. Now get out your calculators and hit clear twice, because we're going to do two things here at the same time. We now know that wire is only worth 75 amps, right? But now it's only worth 65% of that. So we're going to take 75 multiplied times 0.75. Okay, now if we're looking at the 31016, on the left we have a column for 60 degrees, a middle column for 75 degrees, another one for 90 degrees, and then it starts over again, 60, 75, 90. Those three on the far right are for aluminum conductors. We're going to stay on the left-hand side of this page, and we're going to go down to number 6 on the far left column. That's the size of the wire, number 6. We're using a wire that is 90-degree wire, such as an XHHW. And that means that wire would be good for 75 amps normally, under normal conditions. But we know that this wire is being operated at a higher temperature. So we're going to go over to the duration page, which would be in your code book down at the bottom of the page, right under the ampacity columns. You would have a duration section. And 61 to 65 degrees centigrade, you would have a 65% duration factor. So if we multiply 75 times 0.65, we get about 56 amps, right? Okay. Now, what if it's one of 6 current carrying conductors in a conduit and it's going through a room that is 62 degrees centigrade? Then we would have to take additional duration of 80%. So we would multiply 75 times 0.65 times 0.8, and now what do we have? 80% of about 57 is, about 45 amps. So it went from 75 amps down to 45 amps only because there are 6 current carrying conductors in a conduit and it's going through a 60, 2, 3, 4 degree ambient air temperature area. And you have to rate the wires for the highest ambient temperature in the run. Okay. Now, is this what we do in the field as electricians? Absolutely not. Are we trying to find what ampacity the wire is now good for? That's too late, right? We know that we have, let's say, a 5 horsepower motor, and we need to know that it has so many watts of power it's going to crank out, and it's got so many amps going in, and it's got so many volts going in, and the apparent power is this. We've got to supply that, right? And what part of that is important? The amps. So let's say we have a motor, and it's going to draw 52 amps. All right? Now, that's what we need to supply to that motor, right? And we need to supply it without too much voltage drop, by the way. Now, we need to supply it 52 amps. Now, we never size the wire exactly for the number of amps, the maximum number of amps we need. We always build in a safety factor of 80%. We only use 80% of the ampacity, or we upsize the wire for the ampacity 125%, which is the same thing. So 52 times 125 is what? Okay, so we know we're going to need 65 amp wire, right? Now, are we going to try and do trial and error and do a bunch of things and figure out, well, this is the cross-sectional area of wire we need? No. We're going to say 65 amps divided by, now we know we're going to have 3 current carrying conductors or more. We're going to have 6 current carrying conductors in this one particular conduit. So we're going to multiply it times 0.8. We're going to divide by 0.8 to get the higher number of amps we actually need. And also we have a 60, what was our previous duration factor? 0.65. So let's say that we need 65 amps and we have an 80% and a 65% duration factor that we know about. We know we're going to go through a hot area, so we find the duration factor for that. We know we're going to put 6 current carrying conductors in a conduit, so we're going to allow for that. So now what ampacity wire do I need? 65 divided by 0.8 times 0.65 is going to give us a number. Okay, so now if we divide 65 by the quantity 0.8 times 0.65, it will give us 125 amps. So we know that we're going to have wire that would normally carry 125 amps. That's what we do as electricians. We figure out what we have to use to supply the load, right? So now we know we're going to have to select wire that after it's derated, it will still give us our 65 amp availability, so that even if the motor runs for 3 hours in a day, it will still live, because a continuous duty motor has got to be supplied 125% of its full load ampacity. All right. Let's talk briefly about the current carrying conductor chart, which is 31015B3A. It used to be a different place in the code book, but it's a chart that is right before the 31016 chart in every code book. If you go about 1 page before that, you'll find this little chart. And It's the number of current carrying conductors in a conduit and the duration factor for each. So if we had 12 current carrying conductors in a conduit, it would only be good for 50%. That's correct. Okay, and if we had 22 current carrying conductors, each conductor in there would only be worth 45% of its original ampacity, less than half. That's why you have to watch how many current carrying conductors are in a conduit. Now that brings up another question, doesn't it? Every time we come up with an answer, we come up with another question. How do we know which ones are current carrying conductors? If we have a 110 volt circuit that goes out and comes back, is the neutral a current carrying conductor or not? It is, because all the current goes out and all the current has to come back, right? What about a neutral in a 277 three-phase set where you have one neutral and 3 hot conductors going to a 3-phase load? What comes back on the neutral? Only the imbalance, and generally speaking, 3-phase loads are set up so that they're balanced, so you can consider that as a 0 load, or a very small load that can be ignored, more or less. Okay, unless you have an extreme imbalance. Okay, so now I'd like to do a voltage drop calculation real quick, just to show you how this works. Let's say that we have a little light and a little motor on a circuit, and it's single phase 120 volts. And let's say that we have, say 300 feet. Oh, we used 300 feet before, that's all right. And we're going to draw, now this time we're going to go to the limit of a number 14 wire. Let's look at our chart, look at our first chart in our book about wire size, and look on the 60-degree column in a number 14. What is the maximum ampacity for a TW wire, a number 14? What is its maximum ampacity? How many? 15 amps. Is that what it says? That's 60 degrees. Okay, we're going to use that because we're going to use TW wire. If you use TW wire, or this is getting a little ahead, but one of the limiting factors is the temperature rating of the terminals of the equipment. And if the equipment is not stamped 90 or not stamped 75, then you've got to use the 60-degree temperature rating for the terminals. That means that you can only use the 60-degree column for the wires. Even if they're higher ampacity wires, if the terminals are not rated for that higher ampacity, you may not use that wire at its higher temperature rating. Okay, is that clear enough? Okay, so like, let's say I have THHN, which is either a 75 or 90 degree wire. It's one of those. Look on the chart and tell me which it is. THHN, 90 degree wire. Now, if the terminals of the equipment are only 60 degree rated, in other words, they're not stamped, what ampacity, now let's go back to our number 6 wire, that's THHN, that would be good for 75 amps if the terminals are rated for 90 degrees, right? What if they're not stamped at all? Then we have to use that wire at the 60-degree column. So we have to follow that line across to the left, to the far left. What is the ampacity of that wire now? 55. We just lost 20 amps because of the terminal ratings, right? Okay, very good. Now let's go back to our voltage drop problem. And we're going to say that we have TW wire, and that it's rated at 15 amps, but we only want to use 80% of that. What is 80% of 15? So we're going to say that our load, our whole entire load, is 12 amps. And we know that 12 times 1.25 just happens to come out at 15 amps, right? So we know that our load that we have to supply is 15 amps because there's a motor out here. Motor loads have got to be, you've got to go 125% of the ampacity. So we're going to assume that the whole load is motor load. But anyway, we're going to multiply times 125%. Now, as before, we're going to have a temperature rating. So let's go to that page in our book that has the temperature durations, which is 326. And let's say that we have a 50 degree centigrade duration factor. Now, I have a question. We have THHN, right? It's a higher ampacity wire, but we're using it because of the terminals at the 60 degree column. Do we have to use the left-hand TW duration factor or the THHN duration factor? The duration factor is dependent on the insulation type, and therefore the THHN column is the duration factor we'll use. So we're going to use 0.82. And we're going to say that it's one of 6 current carrying conductors, so we know that we have another duration factor of what? 1, 2, 3 for free, 4, 5, 6, 80%. So we have another 80% duration factor. So if we have 15, let's get this out of here, 15 divided by 0.82 times 0.8, let's put the parentheses to the left of the 0.82 and to the right of the 0.80. And so we have 15 divided by the left parentheses, 0.82 times 0.8, right parentheses, enter, and what do we have? 22.87, is that right? In other words, 23 amps. So we need a wire that will carry 23 amps. 14 will no longer do at 60 degree column, will it? Now we've got to go up to what wire size? Back to the first chart, which would be 31016 in a code book. In the far left column, we would have to use number 12, which is good for, no, we can't use number 12, can we? That's good for 20 amps, not 23. So we've got to go up to number 10, which is good for 30 amps. Is it okay to go to bigger wire? Is it okay to go to a slightly smaller wire, even if it's just the tiny, smallest amount above? No. Go big or stay home. Okay, so we're going to use 30 amp number 10 wire. What will using a larger wire do? It will help us reduce our voltage drop, right? Because what we're avoiding here is excessive voltage drop, or what is voltage drop, by the way? Voltage drop is just you're paying to heat the wire, right? How many people want to pay to heat the wires in their house? I don't want to pay for that. Nobody wants to pay for that. That's a useless expenditure of energy, right? We don't want to do that. So as much as possible, we want to eliminate voltage drop. Okay, now, hit pause one more time. Okay, now let's do a voltage drop calculation where we're actually going to find the number of volts dropped, because we're going to go out our 300 feet, but we're going to use size number 10, which just happens to be 10,380 in cross-sectional area in circular mils. That's 10,380 circular mils. So let's multiply 2 times 10.8 times 15 times 300, all divided by 10,380. Let's find our actual voltage drop. Okay, now what we just figured out was that 2 times 10.8 times 15 times 300, all divided by the 10,380, is not going to give us satisfactory voltage drop. It's going to have excessive voltage drop. What that tells us is the wires are within their ampacity rating. That doesn't mean that it's going to be okay for voltage drop. Okay, so for voltage drop, we need to have it even a little bit bigger because it goes out 300 feet. Okay, so let's do that now, and let's find out what cross-sectional area we want to have. Now let's assume that we're coming from a sub-panel, and we only want to lose 3%. Our circuit we designed before was 120 volts, right? So let's do 2 times 10.8 to kill. It's still a 15 amp circuit times 300 feet, all the same stuff, except now we want to find the cross-sectional area of the wire we need to use to eliminate our voltage drop. So we're going to, what's 3% of 120? Okay, so if we plug all those numbers in to our calculator, 2 times 10.8 times 15 times 300, all equals, and then divide by 3.6, we're going to get a new number. Oh, I just stopped the damn... No, I didn't. It's still going. Sorry. I thought I'd stopped the recorder and forgotten to restart it. Excuse my language. Sorry. So, 2 times 10.8 times 15 times 300 divided by 3.6 is 27,000. How many? 27,000 even? Cool. Okay, so now if we had a code book, we could go to the back of the book under what's called Table 8, Chapter 9, and we could look up the cross-sectional area of a wire that has 27,000 or more circular mills. And we're going to find that it's a little bit bigger than a number 10. It might be a number 6 or a number 4. But when we find that, we will know then what wire size to actually use to eliminate our voltage drop and have all our wires within their ampacity rating. So those are two different issues, and now you know how to deal with both, right? Let's do one example for the voltage drop with the 3-phase. Let's do that real quick. Pull up another slide. And let's create a problem where we have 3-phase. We're still going to use 10.8. We're going to have a motor load pretty far out there. It's going to draw, say, 52 amps. Okay, and we're going to put it out, let's say, 250 feet. Now, this is a 277 480 load. Okay, we're going to say it's 277 480. And this is what's called phase voltage, and this is called line voltage. We're going to take 3% because it's coming from a sub panel of our 480. So what is 0.3 times 480? Okay, so we know that 3% of 480 volts is 13.4 volts. So we want to limit our voltage drop to 13.4 volts or less. So we're going to plug that in here, and then that will tell us the cross-sectional area of the wire that we've got to use to do this. So if we multiply 1.7321, which is about square root of 3. I'm sorry, thank you. There we go. All right, so I had the wrong voltage drop that we're going to allow. We have 14.4 that we're going to allow. And so we're going to multiply 1.732 times 10.8 times 52 times 250. We're going to hit enter, and then they're going to divide by 14.4. Okay, let's go over exact button pushing for the TI-30X2S. Now I want to use the square root of 3, right? Now I know that it's 1.7321 or thereabouts, but if I want to use the exact square root of 3, then I could hit, I always hit clear twice first, by the way, but then I could hit, you see x squared? I could hit second function, x squared, and I get a square root and a left parentheses, and I put in 3, right parentheses, enter, and I get 1.732050808, and on and on and on. Now we have a very exact square root of 3, right? Times, I hit x for times, 10.8, times 52, times 250 is equal to, and I get a very large number, 243,179.9. We're going to divide that by 14.4, our allowable voltage drop. We're going to find that we get 16,887.4. Let me write that down because this number is totally wrong. And so we have 16,887.49. So we're going to call it 16,888 or more. So that means that we have to have at least 16,000 square circular mill. So we know that there is a wire that's right at 16,000. So this is the next wire size larger than that. And I don't know off the top of my head which size wire that is, but I know that that's going to put us in a certain size wire. But any quiz question that I might give you on this chapter, all you need to know is the cross-sectional area. This number right here, 16,887.9 or 49 or 16,888. Either number of those numbers will be just fine. Okay, I think that's almost everything we need to cover in this chapter, except for possibly one more thing. Let me look through the book just one second. Okay, now our chapter talks about parallel conductors, and it has a few of the rules, but not all the rules from the code book. The first rule, I'll just read down the rules. Conductors must be the same length. Conductors made of the same material. The conductors must have the same circular mill area. They've got to have the same type of insulation. They've got to be terminated in the exact same manner with the exact same kind of terminals. And that has several different things. And what they forgot to mention is there's a code a code citation that says you can only parallel a certain size and larger, but since that's not on our code in our textbook, you're not responsible for finding that out because you're in first semester, not second semester. All right, now, I think that's everything you need to know from this chapter, so that's the second part of our Chapter 11 review.